on parallel lines, right? So there was this I1 current, and due to this I1 current, so due to this I1 current, there was this magnetic field, right? We already know that that magnetic field would be in the inward direction. In the right hand side, the magnetic field due to I1 current would be inside, and this would be the magnetic, right? So we saw this thing. So we had this magnetic field inside, and then we had this length of the wire. So then we calculated the force experienced by this wire, right? We calculated the force experienced by this wire, and that we calculated as. So then we calculated the force per unit length as this thing. So you got disconnected, Aisha, right? In the last time you got disconnected at the last. So this was yeah, this was the thing that we did. So let me just recall this thing, right? So if we have two wires, they are in the parallel direction. So they will feel the amount of force, and that force would be attractive because they are in the same direction. And that amount is mu naught I1, I2 by 2 pi, let's say distance between them is A, and then this N. So force per unit length would be mu naught I1, I2 by 2 pi. This was the magnitude of force per unit. Okay, so now let us do some question based on this. Uh, so let us do some question, and then this will be more clear, right? Yeah, let us this is the three. We have this question, right? So what is the arrangement of this question? So three parallel straight wires placed perpendicular to a plane of paper carrying same current I along the same direction is shown in figure, right? Magnitude of force per unit length on the middle wire. So this is the arrangement. How is the arrangement? So we have, yeah, let me show you guys the arrangement. So what is arrangement? I can show. So we have this plane, right? We have these plane, and these wires are placed for perpendicularly to this plane, right? So three wires, they are placed like this. So you have these arrangements, right? So one would be the parallel, these parallel wires, right? And let's say this plane is XY plane. So these wires are in Z direction, right? So this is one plane, and then you have these two parallel wires, right? So you have two parallel wires. This one is in the middle at the corner. So this at this P wire we have to calculate the force per unit length, and that would be due to this wire and this wire, right? So what would be the net force, right? So let us calculate that. So as these are two parallel wires, right? So one force would be attracting this B. So this C will attract this B in its direction, right? So one force would be in this direction. And then this A will try to attract this B in its direction, right? So this would be in this direction. So both these would be in perpendicular direction. Right? Let's say this is FC, this is FA, right? And the force per unit length we are talking. So this length. So FC per unit length would be how much? This would be, yeah, so the distance between them is D. And they have same current I, right? All these three have same current I. So this would be mu naught I1, I2 divided by 2 pi A, right? And A is D. So this is one force per unit length. In this direction, let's say that this is I hat direction, right? And this one will have a J hat direction, right? So F A by L. This is again mu naught I1, I2 divided by 2 pi, and distance is right. This is this direction. And we know that these are perpendicular, so net would be in this direction, right? And these are perpendicular, so F net divided by whatever is magnitude we are calculating. So that would be root of Fc by L square plus Fa by L square. So that would be the net force per unit. So let us calculate that. So this would be mu naught and I and I. So I1 and I2 are equal. So this is mu naught I square divided by 2 pi d and whole square plus this is mu naught I square by 2 pi d whole square. Right, both these values are same, so we can write this as 2 into mu naught I square divided by 2 pi d whole square. So we can take this whole square outside, so this would be mu naught I square by 2 pi d, and this is so this yeah, right. What are options? Mu naught I square. So this will cancel. So this would be mu naught I square by 2 pi. So this would be the answer. Is this thing clear, everyone? Is this thing clear? Yes, guys, this thing clear. So if you don't have any doubts, please note it down, and then we'll move on to the next question. So please note this thing down. Yeah, you guys please. And whenever you guys want me to slow down, yeah, whenever you guys have noted it down, please tell. Yeah. Okay, so Rabia, what about you? Yeah.
Sir, can you explain me the explain? Can you explain this again, please?
Oh, yeah. So what did we? So did you understand the picture? Did you understand the
Yes.
setup? Yeah. So we have three, right? We had three. Let's say. Okay, so we had three parallel wires, right? I cannot. How? Yeah. So we had these three parallel wires, right? And first would be due to this contribution, right? So let's say this is in the middle. This is at the corner. So this is B, this is A, and this other one which is perpendicular, so this is C, right? So this A wire will attract this in its direction, right? So one force, attractive force would be in this direction, right? And then we have this another one. So that force, so this wire will attract this B in its direction. So we have one force in this direction, we have another force in this direction. Both are what? Both are perpendicular to each other, right? And we know the force per unit length of this thing, we know the force per unit length of this thing, right? These two are perpendicular, so net force would be what? We already know that from vectors, what do we do? Yeah, good that you asked, right? Okay. So whenever we have two vectors which are perpendicular to each other. Now you know that why these are perpendicular. Did you understand that part?
Yes, sir.
So these two vectors, let's say this is F1, this is F2. These two vectors are perpendicular. So from the resolution, from the net resultant, we know that F net would be F1 square plus F2 square plus 2 F1 F2 cos of theta. So this theta is the angle between F1 and F2. We already know that how much is that angle? Theta is 90. So this will 1 square plus F2 square, right? We know that from our result, we know that what is the force per unit length between the two parallel wires. This we know already. So we have used that thing. We calculated FC, right? Which is mu naught I1 I2 by 2 pi t. And we know that these two currents are same. So we have put that value. Similarly, we calculated FA, force per unit length by force per unit length experienced by this B due to this A, right? So that would be again mu naught I1 I2 by 2 pi t. So we have these two force per unit length and we want to calculate the net one. So these are perpendicular, so net would be just square of these, right? So we calculated this and then we got this. So is this clear now, Rabian?
Yes, sir.
Good. And did you note down this part?
Just a sec, sir.
Okay. Let me zoom this one. Yeah. So when we can imagine those pictures, right, then the problem solving part is quite easy. We have to just figuratively imagine what is happening to those condition or informations. That is one part.
Done, sir.
Yeah. Okay. So now, now let us do another question based on this idea. So the same idea, but different kind of question. This I will delete this. It is this question. Yeah. So the next question you guys will do and tell me the answer, right? This question I will let me do that. But after this question, right? Okay, so this is the next question, right? So what is the question? So a square loop ABCD carrying a current I is placed near a coplanar with a long straight conductor XY. Carrying a current I, the net force on the loop would be, right? So we have to find out the net force on the loop, right? So let's say that we have a XY length wire, right? And let's say that its length is, so this current is I, and then we have this square loop ABC carrying a current I is placed near a coplanar with a long straight conductor carrying a current I, right? Oh, so this one is the long straight conductor. So this one has current I, and this one. So this thing has a current which is ABCD. So let's say that this is A, B, C, right? And let's say that this distance, right? So let's say that this distance, this information is not given, right? So the distance between A and this thing is L by 2. And this is a square, so this is L, this is L, this is L, this is L, right? And the current is passing in this way. So this is the direction of the current, and what is the amount of current that is I, right? So we have this ABCD loop, and it carries a current I, and this one is I. both. So this ABCD is in this is a coplanar, right? What do I mean by coplanar? So let's say that if this is my current, so this is coplanar, right? This is not like this one or like right. So this is a coplanar. They have the same plane, right? So now we have to find out the force acting on this loop, right? So we already know that force between parallel wires, right? Force between parallel wires is that we know already. So this is mu I1 I2 L divided by 2 pi and right. This thing we already. So and we know that this BC. So this is the same distance and these are making an angle. So these are also perpendicular, right? So these are perpendicular and they will have equal contribution. So FBC and FAD will have equal contribution but in opposite direction. So these forces will cancel out, right? So only the forces which will contribute are AB, FAB and FCD. Only these two forces will contribute. So let us find out what would be this FAB. FAB, and I will write the vector, right? So FAB would be how much? This would be mu naught I and and this length is L, and this length is L by 2. So 2 pi L by 2, right? And what would be the direction, guys? What would be the direction? Can you tell me? What would be the direction? Let's say this is x-axis, this is y-axis. So what would be the direction, guys? Yes. What would be the direction? The force would be attractive or repulsive. What kind of force there would be? What kind of
Atlantic.
attractive? So this wire will try to attract this loop. So this is what direction? Minus x. Minus x is what direction? Minus I hat, right? So minus I hat is the direction. Okay, so now we have this thing, this 2 and 2 will cancel. And oh, let us keep this at, right? So this will come in handy in our calculation. So this 2 will go in the denominator and this L and this L will cancel. So we have mu naught I and this is 2 pi and this is right minus I. So this is FAB. Similarly, what would be FCD? You guys tell. What would be FCD? Its length is L. So what would be FCD, guys? Yes. We are calculating the force between this wire and this wire. So we know that force would be mu naught I1, I2, and this length L divided by 2 pi and the separation between the wires. How much is that? That is L by 2 plus L, right? So that is 3L by 2, right, guys? And what is the direction? You see that these are in opposite, so they are not parallel. This one is in this direction, this one is in the opposite direction. So force would be attractive or repulsive. Yeah, if they are in opposite directions, so force is repulsive or attractive. That we have already discussed it here, right? So we have already discussed that have opposite directions, so force is repulsive, right? So force would be repulsive. So force would act in this direction. Okay. So the force will have a this direction. This is how much? FCD would be mu naught I L will again cancel, and we have so we have 2 pi and 3 and 2 I hat. So F net would be how much? F net would be resultant of these two. This plus this. So this is mu naught I and 2 pi and 2 minus I hat 3 I hat. So if we solve this thing, mu naught I by 2 pi, right? So this would be how much? This would be mu naught I by 2 pi, and this is 6. So 2 minus 6 by 3 I hat. So this is mu naught I minus 4 divided by 2 pi 3 I hat. So this 2 will cancel, and we will get the magnitude as mu naught I 2 by 3 pi in minus I hat direction. So this is F net. So magnitude is how much? This is 2 mu naught I by 3 pi. This is the magnitude. The answer would be how much? 2 mu naught, yeah, mu naught I by 3 pi, right? So this is looking like L. So this is, yeah, right. So did you guys understand this part?
Yes.
Yes, is this question clear, guys? Yeah, if it is clear, then you guys please note it down, and then so then we'll understand about the next topic. Yeah, whenever you guys want me to scroll, please.
That's
Yeah, noted.
Yes, sir.
Yeah, Aisha, what about you? Noted?
Yes, sir.
Yeah, whenever you guys have noted it down, please.
None, sir.
And Rabia, what about you? Do you have any doubts?
That's
Yeah. Okay, good. So the next topic is torque on a current carry. Right. So if we have a current carry, right, let us first talk about the magnetic dipole. So what is the magnetic dipole moment? So let's say that if you have a current carrying fluid, right, in this plane, so let's say the current is flowing like okay. So this loop will have a magnetic dipole, and that let's say it has n number of turns, right? So it has n number of turns. So let's say it has n number of turns, and the current is flowing like this. So magnetic dipole moment is defined as Ni, right? So this is how the magnetic dipole is. And the direction of this magnetic dipole moment is defined by this Maxwell's thumb, right? So if we curl our finger in the direction of this current, right, then the direction of the thumb will give us the direction of this magnetic dipole. So can you guys tell me what would be the direction of magnetic dipole moment for this loop, inward or outward? What would be the direction? Yes, what would be the direction, guys? What would be the direction? Yes,
outward.
outward. So outward, which means that it is coming out of the screen. How is it going into the screen? Yeah, outward or outward. So Aisha, what did you say?
Okay.
Outward.
It's correct, out of the space.
Yes. So it is coming out of the screen. Okay.
Yeah.
So the square root is going like this, right? So if we curl our fingers, what is the direction of our point? Is it outwards or coming out of the screen or
Yeah,
going?
it's
It's
coming out of the space.
coming out of the screen. Why? Why
Okay,
is it?
never mind. Okay, inwards. Yeah.
Yeah, inwards, right, Aisha?
Yeah.
So the direction of magnetic dipole would be cross, right? So we represent the inward direction with cross. We represent the outward direction with this point, right? So this is down. Okay, so let's say the magnetic loop is in this, right? This is the plane. So then what would be the direction of the magnetic loop? So that would be, okay, so this is going like this. So magnetic field would be, magnetic dipole movement would be this time, right? This is the magnetic dipole. If the current is going like this, right? So if the current is, let's say this is the loop, and the current is going like, right? So it is going like this, so this should be right. And if it is going like this, it should be left, right? So that would give us, so from Maxwell right hand thumb rule, we can get the direction. Okay, so this is the direction of the magnetic dipole. And let's say the magnetic field is passing through it, right? So let's say some magnetic field is passing through this. So then this will create a net torque, right? Because if we have for a loop, right? For a loop, and if we can, so magnetic field is passing like this, right? And the current is passing like this. So it will experience some net torque because F net would be zero, right? One would be in this direction, the other would be in the same amount. So both will have the same amount of force. So F net in a closed loop is zero, but it will have some net dipole. It will have some net torque, and that torque is given by M cross. So if we take the analogy from electric field, right? If we take the analogy from the electric field, so what was the torque due to external electric field in this dipole? In this dipole, do you guys remember what was the torque? Torque in the external electric field, that was P cross E, right? Similarly, we have a net torque in the presence of magnetic field, and that is M cross B. This is MB sine theta n cap. And n cap is given by this M cross B using the cross product, right? So this is the net torque experienced by the, right? Net torque experienced by the, right, current carrying. So let's say this current is, yeah. So now we will do some kind. Oh, who got disconnected? Learnivio got disconnected. So you guys please note down these parts, and then we will do some question based on this. Please note down this part, and then we will do some questions. Whenever you guys want me to scroll down, Yeah, whenever you guys want to slow down. Yeah, noted, guys.
Done.
Yeah. Then, yeah. So then let us do some question to understand. Yeah, this question we didn't do, but this you guys can calculate, right? We can do this problem and let's see, yeah. So you guys please find the answer of this problem. You guys calculate and then we'll do the other kinds of calculation, right? So we have this rectangular quad and then we have this quad, right? So yeah, please calculate this first and then we'll do other problems. So please calculate and tell me guys how much you guys are getting. We have two parallel wires. First, so we have two parallel wires and at a distance 1 meter, and both of them carry 1 ampere current. The force of attraction for your athlete, right? So this you have to find out. F, right? That yes, Aisha and Rafi, what are you guys getting? This question you have done in your CBSE course, right? When we're doing this, this is a very peculiar thing. This is some kind of, if you remember, this is something important. Yes, guys, what are you guys getting? So 2 into Yeah, wires are 2 into 10 to the power minus 7. So Aisha got 2 into 10 to the power minus 7. What about you, Rabia? What is your answer? So Aisha got this answer. What is your answer? Yes,
Option B.
option B. So you are getting this answer. Okay, so let us try to find out. We know that force point length is mu naught I1 I2 divided by 2 pi, right? So this is 1, right? This is 1, 2 pi, and this is 1. So what do we know? We know that mu naught by 4 pi, that is 10 to the power minus 7, right? So if we multiply this by 2 divided by 2, so we will get what? So this will be divided, right? Yeah, so, okay. Yeah, so what I should write is that, yeah, so this is mu naught by 2 pi, right? Let us multiply it by 2 divided by 2. So this is mu naught and 2 divided by 4 pi, right? Mu naught by 4 pi is how much? That is 10 to the power minus 7. So this would be, and this is force point length, right? So Newton per meter. So did you understand this part, Rabia? Yeah, how did you get it?
Yes, sir.
How did you get 10 to the power minus 8? Yeah,
Sir, I don't know. It was a calculation
yeah,
mistake, I guess.
yeah. So there must be, because this value is 10 to the power minus 8, right? We have to remember this. Okay, and this thing you guys have seen in the definition of 1 ampere current. So the direction of 1 ampere current comes from here. You have two parallel wires. They are carrying the same current. Their separation is 1 meter. And if you measure the force between them, and that happens to be this quantity, then the current amount of current would be called 1 ampere. So this is the definition of 1 ampere that we have talked about in CBSE, right? You guys remember? This is the definition for 1 ampere. Okay, yeah. So let us move on to the next thing, and now let us find out. Yeah, so now let us do this. So a rectangular coil of length 0.8 width having a 50 turns of wire is suspended vertically in a uniform magnetic field of strength this. The coil carries a current of 2 ampere if the plane of the coil is inclined at an angle of 30 degrees with the direction of the magnetic field, right? So plane of the coil is inclined. Yeah. So this this is a coil, right? And let's say this is the magnetic field, right? and the coil is inclined at, so this is the angle, and the coil is inclined at this side, right? So we know that this angle is 30 degree, this is given, right? But what is the angle that we want? So this is the normal, right? The normal to the plane would be this angle, right? The normal to the plane would be this, right? And that is making an angle of how much? That is making an angle of 60. So we don't calculate the angle of the plane. We calculate the angle of the normal and the magnetic field, right? So this angle is 60 degree, right? The angle between the magnetic field and the dipole, that is 60, right? This is this thing. And we know that how much is the dipole? That is N I A, right? So N number of turns is given, and amount of current is what? 2 ampere. And then we have area, right? Area of this square. So area of this square, this is a rectangular, so that would be length into breadth. Length is how much? 0.12. Breadth is 0.1. Right. So this is how much? 110. So 12 by 1000. So this is the 8. 12 by 1000. This is our dipole moment. Who got disconnected? So this time Rabia got disconnected. This is our dipole moment and the torque, right? The torque required to keep the coil in the stable equilibrium, right? So torque would be how much? That would be M cross B, right? And this is MB. Yes, this is MB sine theta. We know that what is this theta? M we have calculated, right? B we know, B is how much? 0.2 Weber per meter square, right? And then we have this sine of 60. Right? 50 into 12 divided by 1000 and it is by 10 again. Sine 60 is root 3 by 2. Right? This 2 will cancel. This 0 will cancel. And then what do we have? So then we have 12 5s are 60 and then 2s are 120. So 120 and root 3 is 1.7, right? So how much is that? This is 34 and this is 17 ones are. So 17 ones are and 30, right? So let us multiply. 34 and 7 is 4, 0. So 204, right? So this would be 204 and divided by this 1000. So this is how much? This is 0.204 nanometer, which is equivalent to 0.2. So this would be the answer. Right? Is this thing clear, guys? Is it clear?
Yes, sir.
Okay, then please. Can you guys please note it down? Yeah, whenever you guys have noted it down. Yeah, whenever you guys have noted it down.
Niranjan.
Noted. Yes, Rabia, what about you? What about you, Rabia? Oh, Rabia got, yeah, Rabia is correct. So, Rabia, did you note it down? Yes. Yeah, I guess. Yeah. Then let us. So a coil is in shape of equilateral triangle of side L is suspended between full pieces of a permanent magnet such that F is in the plane of the coil. If due to a current I in the triangle, a torque acts on it, the side L of the triangle is, right? So we have to find out the side L of this equilateral triangle. So how much would that be? Let us find that out. right? So we have two permanent magnets, right? We have two permanent magnets. So one is this and one is this, right? Let's say this is north, south. So magnetic field is flowing like this, right? This is the direction of magnetic field, and in this plane we have this current carrying, right? So we have let's say the current is flowing like this way, right? Its length is L and current is I, right? I current is in the triangle, right? So this is in the loop, and if we draw the direction of the magnetic moment, so what would be the direction of magnetic moment if we use the Maxwell's rule? What would be the direction, guys? What would be the direction? What would be the direction, guys? So if we curl our fingers, so that is inwards, right? So magnetic field is inwards, right? Ma- magnetic dipole moment is inwards, and the magnetic field are crossing right. Magnetic field are in, let's say, uh, I hat. So this is I hat, cross is minus k hat. So both are perpendicular to each other, right? So theta is how much? That is 90 degrees. So we know that magnetic dipole, that would be NIA. And we have only one term, so N is 1, I is I. Area of this equilateral triangle, that is how much, right? So calculate the area of the equilateral triangle. We know that if we have two sides and the angle between them, right? So what is the area of this triangle? Do you guys remember what is the area of this triangle? Yes, guys, what is the area of this triangle? If you know the two side, adjacent sides, you know, and then angle between those sides. What is the area? Area of triangle is half AB sine theta. So that is the area of triangle if we know those two sides and the angle between them. This is one thing. And we have this triangle which is equilateral triangle. So now we know that the angle between them is 60 degrees, right? This is an equilateral triangle. This length is LL. So if we calculate the area, that would be half L into L and sine of 60. So this is L square, sine of 60 is root 3 and 2 into 2. So this would be root 3 by 4 L square. So that is the area of the equilateral triangle. Right, so area we know, this is I root 3 by 4 L square. This is the area, and we know that torque is tau, right? So torque is mp sine theta. We know that this is 90, so that would be 1, and mb, right? So this is torque. So we know that how much is this m, so this is root 3 by 4 and L square, right? and B is B. So we want to calculate this length, right? The side L of the triangle. So this length square is 4 tau by I root 3 B, right? So this L would be how much? Root of this thing. So what are the options that we have? 5, 3. So 2 we can take outside, right? So 2 is outside and tau root 3 I power. So this is the length of the side. What is the correct option? Is this thing clear, guys? Is this
Yes,
thing yeah, then please you guys write it down. So you guys please note this down and then we do the next question. Yeah, whenever you guys want me to scroll down, please
we can scroll.
all we have all the answers. Oh, this is completed. Whenever you guys have completed, just
Done.
done. Okay, so now the very very tough question, right? So we have a very tough question. You please tell the answer of that question, right? So this question we have done. So current is flowing in a coil of area A, number of turns n, then magnetic moment of the coil M is equal to. What would be the answer, guys? This is a direct question, right? So it's very tough question. Okay, so now this part is done. This topic is. So now let us understand next topic, which is moving coil galvanometer. Why this is so. Now this is so moving coil galvanometer. So what is the structure of what is the key idea of moving coil galvanometer? So I know you guys already know those diagrams. So we had this soft core, and these two magnets are placed, and this one has a right arrow, and this has some winding, right? And the magnetic field is going radially, right? So the magnetic fields are going radially. So we calculated that, and this has some angle, right? So this was the structure of moving coil galvanometer, and we know that there was this coil which was connected, right? So if we move this thing with some angle, then it will create a net torque, and that torque was angular. So this torque was equal to mb, right? And yeah, so we know that this torque is restoring torque. So then we calculated that this was as like the restoring force, which is kx. So similarly, we have a restoring torque, which would be k. This is linear, so this would be angular, right? So let me write it as phi. So this was k phi, and this is m. So then we calculated this m as nia b, and then we calculated this deflection angle. This was the idea of the moving coil galvanometer, right? And then we calculated two things from it, right? One thing that we calculated was the current sensitivity, right? So we calculated the current sensitivity when we take this I in the left hand side. So this was called the current sensitivity, right? This was the current sensitivity, right? And then we have this is current sensitivity, and then we had this voltage sensitivity also. So what was the voltage sensitivity? So phi was NIA B by K. And we know that current sensitivity is phi by I. So what would be the voltage sensitivity, guys? What would be the voltage sensitivity? Yes,
Limited B.
phi by B. Absolutely correct, right? So this would be phi by B. So we have to divide it by. So phi by B, this would be how much? N I, let me write it this way. This would be N A B by K and I by B. So we know that V I R, right? And for the case of this galvanometer, we represent the resistance of galvanometer as G. So V by I would be how much? That would be G. So if we put this value in here, right? So if we put that value in here, so that would be G. So this is the voltage, right? Okay, so this was about the galvanometer, and it had different purposes, right? One is that we can change this galvanometer into ammeter. So ammeter from a galvanometer. And how did we do that? We added or connected shunt resistance in series or parallel. Do you guys remember? How did we connect this shunt resistance? To the parallel to the galvanometer or in series with the galvanometer? Yes, because the resistance of this galvanometer was so high that we didn't get the proper reading of the ammeter, right? We cannot measure just using this galvanometer. So then we added this shunt resistance to measure properly the current that is passing through the conductor, right? So how did we connect this shunt resistance? You guys have
Parallel.
got it parallel, right? So we calculate, yes, absolutely correct. So we connected parallelly to this galvanometer a shunt resistance. So we connected, this is a galvanometer, right? And yeah, let me write it as G. So this has a resistance G, and the current which is passing through this galvanometer is G. And then we connect a shunt resistance S to it, right? And this whole setup is then called an ammeter. So because this shunt resistance, this is an ammeter, right? So this is an ammeter, and this shunt resistance is so much low, right? So this shunt resistance is so much low that this carries all the current. This galvanometer has a very high resistance. So if we have a high resistance, then current will not pass through it, right? Major current will not pass through it. All the current will pass through this side. And if we use, let's say the I current is following through this circuit. So we know that IG is very small. If we use the junction rule, right? So what should be this current, guys? If we use the junction rule, what should be the current? Yeah, so the current is going like this, right? So we have an incoming current I, and then IG and let's say X current is there flowing, right? So incoming is I, outgoing is IG plus X. So what would be x? X would be I minus ig. Clear, guys? Yes.
Yes, sir.
So this would be I minus ig. Okay. Now you guys see that these are connected rows. Yes. Then we'll talk about this later. So I will stop it here and I will do this part in next class and then we'll do this fifth chapter. So this fifth chapter will be done. That will take only one class. That will be completed very quickly and then we'll quickly finish all those stuff. So you guys please note down this part, right? So you guys please note down this part and yeah, please quickly note down this part. So you don't need to draw this diagram, right? Just remember that what is the idea of moving coil gravity. So the torque is equal to the restoring torque. That is the idea. Guys, please note down this thing and in the next class we'll complete this one. Whenever you guys have noted it down, please tell. Done. Okay. Then please, yes, that part I will discuss in second. Yeah, whenever you guys have noted it down, please tell. Yeah, noted, guys.